So I'm back for my fourth installment. Should be the final video for radical and rational exponents, dealing with these expressions. So dividing radicals and rationalizing denominators, there's two key concepts. You got to rationalize, meaning there should not be a radical left in your denominator. And if my denominator has a binomial, you got to multiply by its conjugate. So let's take a couple examples real quick. First example, 10 that I have for dividing radicals. Just use your eyeballs and see if the denominator radicand divides into the numerator radicand. So you can take 2 seconds to say 40 is divisible by 6. So what I want to do is go ahead and take the 6 and divide it by 2 and get the 3. We took care of the coefficients. And then it's the square root of. We can write this as one radical, because if you go back to the quotient property for radicals, quotient property for radicals said that you could take the square root of the numerator and the square root of the denominator separately. But when I write it back as a single fraction, I know that 480 is divisible by 6. So what I have is 3, the square root of, and then we divide that and let me grab my calculator, and I actually get 80. So now I ask myself, okay, what's the perfect square in 80? There is a perfect square in 80. And I just start doing my mental math, and I know that 16 times 5 is 80. So what I have now is 3, the square root of 16 times 5. So out comes a 4. So what I have is 3 times 4 times 5, which is what's left. And 3 times 4 is 12 times the square root of 5. I'm done with that. All right, so I'll move on to example 11, and I noticed that, again, the denominator radicand can divide into the numerator radicand, so I could just make this one single radical. And then the 7 and the 2, if we just pull it to the side, because that's not divisible, I'm just going to set it up to the side for a second. And I'm going to write one single radical. So I'm going to do the cube root of, and then negative 32 divided by 4. Inside the radical, I actually will have the cube root of negative 8. And this brings me to a key concept. You can take roots of negative numbers as long as the index is odd. You, like, say for instance, I can't do the square root of 25. Not for right now. We're going to do that in the next lesson, which will be complex conjugates. Excuse me, complex numbers. So for right now, you need to know that I can only take roots of negative numbers as long as the index is odd, because I can do 3 negatives and then get a negative number. And the root for this will be negative 2. Because negative 2 times negative 2 times negative 2 is going to give me negative 8. So 7 halves times the cube root of negative 8 is negative 2. And y'all know we talked about making that a fraction. We can get rid of some things, or we can make this negative 14 over 2, which just comes out to be negative 7. Okay, so easy peasy, moving right along. Looking at my next set of examples, this is written as one radical. So what I would do is apply the order operations, which means I'm going to just go inside the radical, not order operations, the laws of exponents, and make sure that we simplify this down based on our laws of exponents. So we'll take the 288 and divide it by 2. So again, I'm going to just write my radical, the cube root. And we know 288 divided by 2. 2 divided by 2 is 1, and this is 144. All right. Now, the quotient rule says we subtract exponents. The question that we typically ask is if it's top heavy, bottom heavy, or neutral. This is clearly top heavy because this has the largest exponent. So that means the final resting place for the j is going to be on the top. And I do 7 minus 2 is going to give me exponent of 5. And then k to the 4th divided by k. Again, this is top heavy situation. and this is just going to give me k to the third. Now we come back in and we do the same thing that we was doing with simplifying radicals. We find the perfect cube in 144, and if we break it down, there is a perfect cube in the 40, and it happens to be 8. And if I actually do some multiplication and work on it, this actually, and I'll do this over to the side, the cube root of 8 times 18 is going to actually give me 144. So if we actually separate this, this will be the cube root of 8 times the cube root of 18. So what comes out of this will be the cube root of 8 happens to be 2. So I pull out a 2. And I'm going to pull out everything I can to start with while I'm writing. So what's left over inside the radical would be the 18. And then we go to the j, and again, don't forget that the index is actually the denominator for this exponent. So I say 3 goes into 5 one time with a remainder of 2, and then 3 goes into 3 one time. And I know it's kind of spaced out, so I have to go in and rewrite it where I got it real close, and you know that this is multiplication. This is 2 times j times k times the cube root of 18j squared. And throw my little box around it, and that lets me know that we're done, and we're moving on to the next problem. All right, so what's my next problem? Okay, so now this is a first example where we don't have a situation where the radicand and the denominator goes into the numerator. So this is where we come into the rationalize the denominator. Since this is a monomial denominator, meaning it's just a single term, what we're going to do is we're going to multiply the top and the bottom by the version of 1, where whatever's inside this radical, we're going to multiply the top and bottom by that. And we know how to multiply fractions. We multiply fractions straight across. So I'm doing 1 here because I'm multiplying. The only thing that I can multiply together is the things that's on the outside of the radical. And this gives me 5, the square root of 10, divided by, and then it goes back to the multiplying rule saying that I can multiply these two radicals together as long as they have the same index, and they do have the same index. So I'm going to do 10 times 10, which is 100. And that's going to equal to 5, the square root of 10, divided by the square root of 100, just happens to be 10. And now, don't forget, always check and see if there's anything that we can do. And we can actually reduce this down. So I focus on the 5 over 10. And I don't put 1s in my problem, so make sure that you don't do that. This is going to give me root of 10 over 2. So I have the square root of 10 divided by 2. And that is my final answer for that problem. All right, moving right along. I can go ahead and reduce this down if you want to, and make that 3 square root of 8 divided by 2, the square root of 3. And there's a perfect square in 8, but I don't want to have to simplify this thing 2 times. So what I want to do is just go ahead and multiply by the square root of 3. So typically most students ask me, hey, do I multiply by the 2? Well, let's think about what it is that we're doing conceptually. We're trying to rationalize the denominator, so therefore we're trying to get rid of the radical. We don't really care about the 2, so we're going to multiply by the version of 1 is the square root of 3 over the square root of 3. So again, we multiply the coefficients on the outside. 3 times 1 is 3, and then 8 times 3 is 24. And then we divide this by 2 times the square root of 9. And we know that the square root of 9 is 3. So this is going to give me 2 times 3. And then there's a perfect square in 24. The perfect square that I have in 24 happens to be 4. So this is going to give me 4 times 6. So this happens to be 3, the square root of 4 times 6. So out comes a 2. So what I have is 3 times 2. Square root of 6 divided by 2 times 3. But hey, look, this is 6 divided by 6. So this pretty much cancel out because 1. And that just gives me the square root of 6. Okay. All right. Next example. This example, and actually, I'm gonna say 15 for class. So if you come into class, we can work on 15 because I don't want to run out of time. And I'm gonna multiply, because this is a binomial denominator. I'm actually gonna multiply by the conjugate, and the conjugate would be this. And what I'm gonna do right now is pause it. And I'm going to go to some side work, and then I'm going to come back to this problem because, again, I don't want to make another video. All right, so I'm back, and let's take a look at this example and what I actually did. So, again, I want to rationalize the denominator, and I'm multiplying this denominator, since it's a binomial, times its conjugate. The conjugate for this would be just changing this subtraction sign to addition sign. And then we multiply that top and bottom. That's my version of 1. And then we distribute the 4 times -1 and get -4. And then 4 times 1 to the square root of 5, we get 4 to the square root of 5. Now, since these are conjugates, we know conjugates multiply to difference of squares. I'm going to square the first thing, put a subtraction sign, and then square the second thing and put a subtraction sign. Now, -1 squared is 1, and then the square root of 5 squared is just 5. And the reason why that is, square root and squares are opposite each other, so they pretty much just cancel each other out, and then out comes the radicand. Simple process, easy to remember. So now what I do is just combine the 1 and -5 and get -4. So what I did was just separated this into 2 separate fractions, because I know -4 divided evenly into both of these numbers. So I did -4 over -4. And then I did positive 4 square root of 5 over -4. And my final answer is 1 minus the square root of 5. All right, so now I want to take a look at this next example. And let's talk about it. I multiplied, because I have a radical here, I multiplied by 5 minus square root of 5 minus 4. So I went over to the side and did 5 times 5 square root of 5 minus 4. Again, we got to do the multiplication. We do the 3 square root of 5. And we get 3 to the square root of 5, and then 3 times -4, and I get -12. And then square root of 5 times square root of 5 is square root of 25. And then square root of 5 times -4 is -4 to the square root of 5. All right, so then I noticed that the square root of 25 is just 5, so I just rewrote it as 3 to the square root of 5 minus 12 plus 5 minus 4 to the square root of 5. This thing and this thing is like term because it has the same radicand with the same index. So what I did was I combined the numbers first, which is -12 plus 5, and got -7. And then this thing and this thing combined was 3 minus 4, which is -1. And again, we don't put ones there. And it gives me negative square root of 5. So I just transported this back over here to my numerator. Now the denominator, again, because these are conjugates, this happens to be the difference of squares. What I did was I squared the first thing, and I got a subtraction sign because it's a difference of squares. And then I squared the second thing, which happens to be 4, and I got that square here. So now if I simplify that, the square root of 5 squared is just plain 5. And then this is minus 4 squared, which is 16. Now, 5 minus 16 is -11. Now, notice that if you look at my final answer and you look at this, and you're probably saying, well, I'm sorry. If you look at my final answer and you're looking at this, you're probably saying, Coach, how did you get from this? Well, it's simple. This is -7 minus square root of 5. And then I also notice that my denominator is negative. The only reason why I'm doing this is because I have a negative number in the denominator. If it was positive, I would not do this. So think about, you actually pull out a -1 because that's a GCF. I pull out a -1, and now you notice that a negative divided by a negative is positive, and then this becomes just 7 plus the square root of 5 as my numerator, and then 11 in the denominator. Since I'm running out of time and I don't want to do an additional video on the rational expression part, we will actually finish in class. There's not a lot to that. It's just pretty much knowing your rules on how to transfer from a radical to a radicand. All right.